Let's imagine a scenario where we like to predict one variable using another variable or a set of variables. For example, predicting the number of views a TikTok video will get next week based on video length, the date it was posted, previous number of views, etc. Another example will be predicting which movies a Netflix user will rate highly based on previous movie ratings, demographics, and other things. So throughout this course, we like to use concrete data, and the first one we're going to use is the advertising data, which consists of sales of a particular product in 200 different markets. An advertising budget for the product in each of these markets for 3 different media: TV, radio, and newspaper. Everything here is given in units of $1,000. Besides the sales, which are 1,000 units, you can see on the table 4 columns in the TV, radio, newspaper, and sales. Now there's an asymmetry in many of these problems. The variable we like to predict may be more difficult to measure, or is more important than the others, or maybe directly or indirectly influenced by other variables. For that reason, we like to define 2 categories of variables: variables whose values we want to predict, and variables whose values we use to make our prediction. So let's look back our data. We have again the table with the 4 columns. Now we're going to agree on the nomenclature we're going to be using throughout the course so we all understand each other. So first of all, the columns that we use to predict, we're going to be calling them predictors, or features, or covariates. And we're going to use the mathematical symbol x for that. The variable we're trying to predict, we're going to be calling outcome, response variable, or dependent variable. And we're going to use the mathematical symbol y. As you can see from the table, there are multiple rows. Every row is an observation. And in general, we're going to have n observations. And every column, besides the sales, is going to be called a predictor. And we're going to, in general, have p predictors. Now, the columns, the predictors, we're going to be also called data matrix. And of course, the response variable, we're going to keep the y. We're going to call it y. Capital letters will mean matrices, and lowercase letters will mean vectors. Now let's connect it with pandas that we already have seen. When we take the data matrix, if we do x.shape, that will give us the dimensions of the data matrix x, should have n comma p. And for the response variable, y.shape should give us n comma 1 or n comma nothing. Just to simplify things, for the rest of this segment, we're going to be talking about one predictor. In the next section, we start talking about multiple predictors. So if we only consider one predictor, in this case, the TV is the TV budget. The x.shape now, the shape of the data matrix should be n comma 1 or n comma, and the response variable, of course, will remain the same, n comma 1 or n. Some distinction in pandas we should be paying attention is if we do data frame double bracket or data frame single bracket. Data frame double bracket will return a pandas data frame, where data frame single bracket will return a pandas series. We're going to need that when we use sklearn later. Okay, now we have decided how we're going to name things. Let's start talking about how we're going to model. What is a statistical model? Now, we're going to make the following assumption. The assumption is that our response variable y relates to the predictor x through some unknown function f of x. That functions express the underlying rules relating x and y. In addition, we add a random amount epsilon, which is unrelated to x, that describes the difference of y from the rule of fx. So the equation there will become y is equal to fx plus epsilon. When we use a set of measurements, xi1 to xip, to predict the value of the response variable, we denote the predicted value by yi with a hat is equal to f hat, given the xi1 to xip. Now there's 2 types of models we can do. The first one is that what is important is obtaining a specific form for f hat, our estimate for f, and these are called inference problems. The other kind is that we don't care about the specific form of f. We just want to make our predictions y hat as close to the observed values y's as possible. We call this prediction problem. Let's go back to our data now. We have again sales versus TV budget. And in the plot, you see all the observations we have, all 200 of them. Our motivation here is to predict sales. We want to build a model to predict sales versus TV budget. To connect to the things we said before, the response variable y is the sales, and the predictor x is the TV budget. Now, to simplify things, I only pick up 8 points, and we have again on the x-axis the TV budget in thousands of dollars and the sales in thousands. The x will be my predictor, the y sales will be my response variable. Now, the goal here is to predict the sales given some TV budget. So we want to find what is the value of the sales at X or TV budget of about $75,000, or what is the sales for a TV budget of about $140,000. Well, the first thing we can do is to come with a very simple model. And for this simple model, what we do, we take the average of all the data we have, all the sales we have for all our observations, and we're going to call that our first naive model. We can extend our model by getting inspiration for our everyday life. For example, if someone asks me to predict something, I'm always trying to think about similar examples I have seen. Imagine a patient going to a doctor with certain symptoms. What the doctor will do is think what other patient has seen today or this week, and the diagnosis will be inspired by the other patient has seen. Now we can take that and apply to our data and our model. What we're going to do, we have our data, and someone is asking what is the sales for TV budget of $175,000. What I can do is see all other examples I have, and I find the most similar one, and that will be my prediction. Now, to find what is similar, we have to define what we mean by similar, and in this particular case, what we're going to consider as similar is the distance of my X, my TV budget I want to predict, to all the other ones. We call this D, which is the distance between the points. At that point, I'm going to find the nearest neighbor by finding the minimum distance to all these other points, and that will be my nearest neighbor, and my prediction now will be the value of sales for my most similar example in my data set. Now we can use that, and we can make prediction for any TV budget, and that's a plot we see now, and this is the prediction of sales for any given TV budget. You can see that we have these horizontal lines because in that region of the horizontal line, the nearest neighbor is the point, the start point, and then when we move to another region, the nearest neighbor will be the other start point. Now we can do this for any number of nearest neighbors. We call k. K is equal to 1 is the one I saw before. K is equal to 3, k is equal to 8, or whatever we want the k to be. You can see for k is equal to 8, and since I only have 8 points, I'm returning back to my original naive model, where I take all the points and I average them. Now let's go and put all the data back to make it more interesting. Now I can do k is equal to 1, and you can see for k is equal to 1, I go through every point as expected. For k is equal to 10, the line becomes a little bit more descriptive, and for k is equal to 70, I'm going closer and closer to the average model. Now, which model is best here? That's a question we're going to answer in the next segment.